Okay, so welcome back, and now we're going to start talking about something under the context, or well, under the title of numerical analysis. Okay, so there are lots of applications in math in the real world where we want to solve an equation. We want to find the zeros of an equation, okay, or the roots of an equation. So we are lots of applications where basically what we're interested in is trying to find the solutions to this equation. Now, for lower degree polynomials, it's easy, right? First degree, second degree, we can find the zeros. Third degree, we can find the zeros. Even with higher degrees, like fourth degree, fifth degree, we have tools that can help us find the zeros of a polynomial. We, like the rational zeros theorem. So we can, use the factor theorem, the remainder theorem. So all these theorems that we've learned in algebra and pre-calculus, we can use to find the zeros of a function. But here's the thing. In the real world, we have some really complicated functions, okay? Fifth degree. Now, for example, in a fifth degree polynomial, there is no formula to find the zeros, like the quadratic formula, right? There just isn't any. Right? For first order and second order polynomials, we have formulas. Anything above that, we don't have any formulas. Okay? And so in a lot of contexts, it's just practically impossible to find the zeros. Okay? So, and that's where techniques like Newton's method comes in. Newton's method is a way of what we call numerical analysis, okay? Or a numerical approximation. So we use this method to approximate or find the zeros, okay? And it's a very quick and easy method, okay? And so we can actually use this method to approximate the zeros to any number of degrees of accuracy or decimal accuracy that we wish. In fact, your calculator and computers do a lot of the mathematics of finding the zeros using this method, okay? So, how does it work? Okay, it's an iterative process. So let's start with a guess. So let's say here's our zero. Okay, and we have, this is our zero, and we'll call this x star. Okay, and let's say we don't know where the zero is, so let's approximate it at x0. So this is our initial guess. Excuse me. So what are we going to do? Well, Newton's method says, okay, this is our guess. So what we're going to do is we're going to use the point on the graph at x equals 0. And what we're going to do is we're going to use the tangent line at that point. Okay? So what we're going to do is we're going to form a tangent line at this point. Now let me see if I can do this straight. Okay? So now, what happens is this tangent line, using this as our initial guess, is going to intersect the x-axis at a point. Now, here's the thing. If the value of that point, right, so we choose this, if the value of that point is greater than 0, then that means it's not the intercept. It's not the 0. Right? So in other words, so we're going to draw a line, right? And we're going to say if the derivative, right? The slope, right? If the slope of this, if the derivative of this function is not equal to 0, what does that tell us? Well, what would the slope of the, if it was 0, think about it this way. If the tangent line was, if the slope was 0, that would mean what? It would mean, what about the slope? It would mean the slope is 0, which means what? That we have a horizontal line, right? If we have a horizontal line, it means that it's not going to intersect the x-axis. It's parallel to the x-axis. So if the derivative is not equal to 0, that tells us that we have a slope that is going, we have a tangent line that is going to intersect the x-axis. And so if it's going to intersect the x-axis, that means it's not a 0. We haven't found it yet. Okay? Now, here it intersects at this point. So guess what? We're now going to use this as their next guess. Okay? So that was going to call it x1. Okay? So it's going to intersect at some point, x1 comma 0. And so we're going to let that be the next approximation. Okay, now, typically, our next approximation is going to be closer to the real 0. So let's do this. Now, what we're going to do is we're going to find the point on the graph. And now this is going to be x1 comma f of x1. And so guess what we're going to do? Now we're going to draw a tangent line at that point. So now let me see if I can do this. Okay, and so now guess what? Now we have another one. Now, so what do? We take the slope. If the slope of this tangent line is not equal to 0, then guess what? It intersects, at another value, another intercept. And guess what? This becomes the next one. And so we keep doing this over and over and over again until we get as close as we want to what the approximate value of the 0 is. Okay, that's the idea behind it. So let's look at this algebraically. Okay? So now, here's what we have. Okay? So we have y. How do we want to do this? So x0 is going to be our first approximation. Then the approximation of x1 is defined as x10, right? Right, that's going to be our next approximation. Now, this is going to be the x-intercept of the tangent line of f at x0, right? So this is going to be the intercept for this tangent line at x0, right? So now we're going to define the intercept in terms of x1, but the tangent line is based off of our initial guess, which is x0. So the equation of the tangent line then is going to be this. Y equals f of x0, right, plus f prime of x0, x minus x0. So this is our equation of the tangent line. So x1 has to satisfy this equal to 0. Excuse me. Because if this is 0, if y is equal to 0, right? So this is the equation of the tangent line, right? So here's the slope at x0, right? That's the slope of the tangent line at x0, x minus x0. So again, so here's the equation of the tangent line that goes to x1. So now, if we set this equal to 0, then our next approximation, x1, has to satisfy it. It does, right? So now, what do? So now what we're going to do is plug in x1. So this means that f of x0 plus f prime of x0 times x1 minus x0 has to equal 0. And then of course if we solve for x1, right? So if we solve for x1, what does that mean? It means x1 is equal to what? It's going to be f of x0 divided by f prime of x0 plus x0. Oh no, hold on. Minus. Yeah, so it'd be negative. So we can rewrite this as x0 minus f of x0 divided by the derivative of f at x0. So this becomes our formula for x1. Now, guess what? Similarly, at x2 comma 0, guess what? Now, if we're looking at this equation line, guess what? Now we have f of x1 plus f prime of x1 times x2 minus x1 has to equal 0, right? Because now if we find x1, we get f of x1 and we form the tangent line here. So now x2 comma 0 becomes the intercept. So that way, when we put in x2, right? Then x2 needs to satisfy this equation. And guess what? Now when I solve for x2, I get x2 is equal to x1 minus f of x1 over f prime of x1. And now, guess what? Now we see the iterative process. We've defined x1 in terms of this formula, in terms of x0. The next one is going to be x2. The next intercept is going to have to satisfy this formula. And then, of course, x3 is going to have to satisfy the next formula, which is going to be x2 minus f of x2 over f prime of x2, and so on. So guess what? Now, we could say, okay, for x of n, for all n greater than 0, x of n satisfies this equation. It'd be x of n minus 1 minus f of x of n minus 1 divided by f prime of x sub n minus 1. And so now, what we're going to do is we're going to see how to make use of this technique to approximate the root of a polynomial. And we're going to do that in the next video. Have a great day.